Hi, everyone. Welcome to the lecture today. Last time we were discussing the topic of user-defined functions. So there's a few things that I still want to go through to kind of continue with the same subject. And on this lecture, we're going to look at continuing the idea of user-defined functions, but also looking at some other important functions that are used to manipulate files. I'm hoping that we'll finish with this topic, at least the core of using functions, and then hopefully we'll get a little more into expanding, I guess, the capabilities of MATLAB when it comes to plots. But in this other subject we're going to be looking at is we're going to be looking more into graphics and how to manipulate graphics and use them, which will be important later when you get into other more advanced topics in electrical engineering. So in any case, let me just move on here. I'm going to share my screen and we're going to pick up where we left off last time. Okay, so this is where we stopped during the last lecture, looking at user-defined functions and a way for finding the number of arguments in a function, number of input arguments, and number of output arguments, which could be important when you manipulate functions. In any case, we now look at more of the user-defined functions. And give me a minute here. Here we go. When we look at user-defined functions, it's important that we understand how functions manipulate variables. There's a concept of local variables and global variables. And when you're designing or writing functions, it's important to know the difference of those type of variables. In essence, a local variable is a variable that is using function files within the function itself. It only has meaning inside the function you're defining. And the only way a function can communicate with the workspace is through input arguments and the output it returns. Any variables defined within the function exist only for the function to use. So for example, if you look at this sample code here, we have a function named g. Remember that the name of the function here is g. And it gives us one output called output, and it has two input variables, x and y. So the function is very simple. It only does one thing. It takes the two numbers x and y, or the two arrays x and y. Those are more than one number. And it simply multiplies the two elements, and it gives you the output of the multiplication. It gives you the result of the multiplication. So in this case, A, as you can see, A contains the result of the multiplication. Excuse me, x and y are the two inputs to the function, and the output is or the variable that stores the output is called output in this case. But in this example, A, X, Y, and output are all local variables, meaning that they only have meaning within the function itself. If we try to do something with those variables, if we call A or output or any of the other local variables, you'll see that you won't find it. If you look in fact, if you look in the workspace, after you have defined the function and saved it, you won't find variables with the name x, y, a, or output, okay? Because those are local. They can be used for additional calculations inside the function g, but they're not stored in the workspace. Okay, so it's important that you understand that, because outside this function, unless it's your purpose that it can be available outside the function, it won't be available by default. The variables won't be available. So And the reason for this is because functions must be completely self-contained. The only way they can get information from your program is through the input arguments. And the only way they can provide information is through the function output, or the output argument. For example, this is a function to find the distance an object falls due to gravity. And again, we call the function, or the name of the function is distance. It takes one input argument t, and it produces one output argument result. Now remember, when you say when you save your functions, you have to give the function or the file that you save it in the same name as your function. So in this case, if we save this function, it's going to be saved under a file name called distance with the extension m, or distance.m. Okay. In fact, if you save it under any other name, MATLAB will save it. But then when you run it, you won't be able to run it because it won't understand what distance is. So saving it, you can give it, by mistake, you can give it other names, and MATLAB won't complain. But when you try to run it, then it won't find it. So it is very important that you save it with the name as the name of the function. But in any case, this function calculates the distance a falling object travels due to gravity. G is defined as a constant of 9.8, in this case, meters per second square. And so the result is simply the, your common expression for finding the distance of a falling object, which is 1/2 g times the time square. So in this example, again, the value of g must be included within the function. It doesn't matter whether g has or has not been used in the main program. How g is defined is hidden to the distance function, unless of course, g is specified inside the function itself. So in this case, g must be included inside that function. Of course, you can also pass the value g to the function as an input argument. For example, here, instead of just using t as the argument, we can give it g also as an argument. And in that case, then it's another way of making that value available. And the result will be computed the same way. All right, so now we talked about local variables that exist only within the function itself, but also global variables. Global variables are sort of the opposite. They're available to all parts of a computer program. Now, it may seem like a good idea, but it is not always the case that you have to use global variables, because it's easy to create other programs, or other problems rather. In general, it's a bad idea to define global variables, period. However, MATLAB protects users from unintentionally using global variables by requiring that it be identified both in the command window environment or in a script and in the function that will use it. The reason for that is because other functions may be using the same names that you are trying to define as global variables, and you may create other problems. So it's not a good idea to use global variables in any event, but they do exist. And they, like I said, they're available to all parts in the computer program. In this case, we have a function, again, the function distance that we defined previously. But now we have defined g, capital G here, as a global variable, okay? Meaning that when you define it as a global variable, it's going to be available for other functions in your programs if you want, okay? So the global keyword here alerts the function to look in the workspace for the value of g. G must also have been defined in the command window or script as a global variable. This method allows you to change the value of g without the need to redefine the distance function, for example, or providing the value of g as an input argument to the function itself. Okay, so it's in this event, in this case, it might be a shortcut, but when you create a global variable, it becomes available to other functions and can be changed by those other functions, sometimes leading to potential problems. So that's why if you have to use them, you have to be very careful about how to use them, and just use them if you really need them, or if it really is a necessity in your program. Otherwise, it may create problems defining global variables. Okay. But by the way, if you ever you notice here that in this piece of code we use capital G, and as a matter of style, if you will, or convention, is always recommended that if you ever use global variables, use uppercase to name them. MATLAB doesn't really care about it, but the point is that it's easier to identify global variables if you use a consistent naming convention for the same reason. Because in that way, if you ever run into a problem, the variable may be changing without you doing anything. Some other program may be changing that variable that you define. Then it's easier for you to find it. Okay, so if you get into the habit, or not the habit, hopefully, but if you get into the need of defining global variables, use capital letters to define a global variable. It's just it's just a matter of style, if you will. It's not a requirement. Okay. So now, if we look at accessing function code, the functions provided with MATLAB consist of two types. One type, of course, is built-in functions, and the code is not accessible for you or us to review. And the other type consists of files stored in toolboxes provided with a program. Toolboxes are very common in MATLAB. There are some very powerful toolboxes for just about any application, and that allow you to do things that are specific to certain applications, like digital signal processing toolboxes. They're control toolboxes. They're communication excuse me, toolboxes. There are several mathematical toolboxes and so forth. And normally what happens is that you'll see those available when you look at your workspace in the command windows in MATLAB, and you look into one of those tabs and you look into the apps tab section. It will list a lot of the toolboxes that you have available. Not all toolboxes will be available in that particular case for two reasons. The one reason, like I mentioned before, is because toolboxes are sometimes specific for certain applications. So if you not really do anything with DSP or controls, then you don't need those toolboxes, obviously. And the other reason is because toolboxes are extra features of MATLAB, and you have to pay for those toolboxes to use them. Okay. So, but we do have several available, and you can see them. Like I said, if you go under apps and you look you'll see several toolboxes that are currently available under our license. But in any case, like I was saying before, this type of files that are part of toolboxes, they can be seen. Okay. And we can see this function file, or the function file written by users, with the type command, type command. So, for example, if you type type cos, then MATLAB is going to respond by telling you COS is a built-in function. Okay, if you type ran, and again use the command type type ran, it'll say, well, ran is a built-in function, meaning that it doesn't allow you to look at it, to look inside, how it's being built. However, if you look at some other functions like sphere that we used previously, which is part of a toolbox, okay? Again, it's an added feature. It's beyond of what the normal MATLAB provides, if you will. Okay, and so if you look at sphere, or there's another function, there are many of them that comes in toolboxes, but another one is IM_read, which we'll see later when we get into graphics. IM_read is used to read images into your programs or into your files. So those type of functions come from toolboxes. And if you do, again, type IM_read or type sphere, then you will see the actual functions definition. You will see everything that comes with that function, how it is defined, what it does, and everything, just like if you were looking at your own functions. Okay, so that's good to know, because you can take you can learn from those functions, and you can take pieces of it if you want, and use them for your own functions if you want. So just remember that you won't be able to see the definitions for built-in functions, but you will be able to see definitions for the toolboxes, just like when you do for your own functions. Another thing that you can do is when you're creating your own toolbox of functions, right? You come up with a group of functions that you have defined or created through the years, or through your times through different applications or courses, and you can create your own set of functions, and it's a good idea to keep them organized, well, and to know where they are. When you call a function in MATLAB, the program first looks in the current folder to see if the function is defined in the folder you're working on. If you cannot find it under the current folder, it starts down through a predefined search path, looking for a file with a function name. And so if you want to know where your functions may be located, or if you may be looking for a function that you defined previously, you used previously, but now you cannot run it because you cannot find it, you can use any of these two commands. If you use the path tool command, for example, we'll see in the next slide, then it'll show you, if you type path tool from the command window, it'll show you the different folders and where MATLAB is saving your function. So the path tool allows you to change, and you can change it, allows you to change where the MATLAB looks for functions definitions. So you can create your own section where, if you get into the habit of writing many functions, and if you want to keep them organized, you can create a folder just for those functions, and you can tell MATLAB where to find them. Okay. All right. I know a couple of lectures ago, we talked about inline and anonymous functions, but I want to go back to this in the context of defining our own functions, and how we can expand on the use of anonymous functions, and also the concept of function handles. Remember, a handle is just a nickname for a function itself. So anonymous functions, remember, are defined in the command window or in the script, and are available just like variable names, only until the workspace is clear, right? So they're temporary, right? Once you clear the workspace, then they're not there. For example, we want to create an anonymous function to generate a vector of random numbers between two numbers, B and A. Let's see, there's a problem here. There should be a parenthesis here, and I'll fix that in the final slide that you'll see. But we've done this before. Remember, when we want to generate numbers between random numbers between two numbers A and B, right? And we want to generate a number of random numbers between those two endpoints, right? We've done this in the homework also, right? So, and the way to do this is by using this expression, right? If you look at the function definition here, B is one end of the set that we want, A is the other end of the set. So we want to generate numbers between B and A and B, and we want to generate a number C of those numbers, right? So C is the number of random numbers we want to generate between A and B, right? Again, we've done this before. But now I want to use this in the context of an anonymous function, right? And you'll see how it can be useful that way. So again, if you remember, this @ symbol tells MATLAB that this is a function, okay? And then followed by that are the inputs to the function. And remember, I'm going to fix this in the final slide, and I'm going to put the parentheses in there, right? Because what we want to do here is just pay attention to the endpoints that are A and B, and the number of random numbers that we want to generate, which are given by the variable C. So in any case, you can see here that we're defining an anonymous function called rand_range that takes three inputs, A, B, C, and it does this. It computes what we want based on this function, right? But it does it in one step, as you can see. So if I define the rand_range function this way, right? By again being careful about the @ followed by the variables I'm going to use and what the variables are going to do, right? And if I run that, right? If I run it once I defined it, whether I have it in the script or in the command line, then if I type rand_range and I give it the variables 25 and 5, meaning that I want to generate 5 numbers, right? 5 random numbers between 5 and 20, right? That's what this definition is telling us here. We want to generate 5 random numbers between 5 and 20. And again, remember, we did this in the homework as a and we type all this, right? But if you want to generate this as a one simple line, you can create this anonymous function. And by doing that, as you can see, the function generates 5 numbers between 20 and 5, right? Given that I define rand_range as an anonymous function. And in this case, as you can see, it's very useful, right? Because I don't have to type all this here every time I want to use that function. All right. So, and remember, I mentioned this before, once you clear the workspace, the anonymous function doesn't exist anymore. Unless you save them, and you can save it as .math files, just like any other variable, and you can restore them with the load command. So for example, save the anonymous function that we just defined, rand_range, you just type save and the name of the function, and it'll save it as a math file. A file name randrange.math is then created, which is going to contain the anonymous functions, or in this case, the anonymous function. Once the workspace is clear, the function no longer exists, but it can be reloaded from the .map file. Again, you can use load ran range, and it'll bring it back. So save will save it. You can clear the workspace, but then you can bring it back again by typing load ran underscore range, or whatever name of the function you've given it. Okay. So you've seen the name handle before. Now, function handle is a specific MATLAB data type that represents a function. It basically is the name of the function. It's the nickname or the name of the function. A typical use of handles is to pass a function to another function. Functions that take a function as an input are called functions. I know it's kind of redundant, but that's what they call. So if you have a function that has inputs that consist of other functions, that function is given the name functions because it uses other functions. Okay, and we'll see some examples in just a minute. You can use function handles as input arguments to functions that evaluate mathematical expressions over a range of values, for example. They can represent, handles can represent either name or anonymous functions. For example, in this piece of code here, we want to find the integral of the natural log from 10 through 5 and pass a handle to the log function to integral here, right? Integral. So integral is calling this function here, log, right? At log, using this at to indicate to the program that what follows is a function. So it passes the variables a and b, and it also tells us to use this function log, right? Which in turn will will compute the integral of the result. Okay, so it takes the log of a and b, and then it computes the integral given those two values, right? And it gives you the result as Q1. So in this case, we call this a functions, right? So this is an example of a function integral calling another function log. Okay. And this is very common, especially in the built-in functions. That's the way they do a lot of the things. They reuse functions, in other words, right? You can imagine many other functions reusing other functions to build on themselves, right? It's something that you can also do with your own function. Another example, we want to evaluate the integral of x over e to the x minus 1 over the range from 0 to infinity. And in MATLAB, if you write INF like this, it represents positive infinity. Okay, it understands that means positive infinity. So in this case, we have this anonymous function fun, and again, it's a function, it's an anonymous function with the @ symbol. It takes on the one variable x and is defined as the x divided by the exponent of x or e to the x minus 1, right? Using the function exp to understand that this is the e to the x function. And then it integrates, it computes the integral of this function, right? See? And since this is already an anonymous function, it understands that this is a function, right? It's going to look for this fun as a, just like a variable that has been defined already here to do this. And it's going to compute the integral from 0 to infinity based on this function. So this is a good example also of how functions are used, right? Again, the idea of a function integral using another function, fun, to compute the result here of the integral. Okay? So it's not unusual. It's very common to use functions within functions. Now, there's another twist to this. Not exactly the same, but also sort of reusing functions that you may already have defined somewhere else, but using them to make your functions either more clear or more or more efficient, if you will. And that's the concept of subfunctions. Okay, subfunctions, in a nutshell, are functions within functions. Okay, they can be created by grouping functions together in a single file. There are two approaches to this. You can add subfunctions to a script, or you can use multiple subfunctions within a primary function. They can be used to make your code more modular and to make the primary code easier to read. Okay, they have this advantage that they're only available from the primary file and cannot be used by other programs. But they can be useful sometimes, and we'll see an example in just a minute. Each MATLAB function has one primary function, right? The name of the M file must be the same as the primary function name, as we already know. So the primary function stored in the M file, my function.m, must be named my function, right? I just made that note a couple slides ago when I said that we have to name the function file the same as the function name, right? Anyhow, subfunctions are added after the primary function and can have any name that a variable name in MATLAB can use. So in the next example, we'll see a very simple example of a function that adds and subtract two vectors at the same time. The function, you call the function, you give it two vectors, and it's going to give you as an output the addition of those two vectors, or the two numbers, and the result of subtracting those two numbers under one single function. Now, again, this may not be the only way you can do this, right? But it shows you an example of how it can be done using the concept of subfunctions. Okay, so we're going to call the primary function subfunction_demo, and we're going to include two subfunctions, one called add and one called subtract. So again, we're going to create a function called subfunction_demo, and within this subfunction_demo, we're going to define two other functions, and the functions are add and subtract. So whenever we define another function within a main function, those functions are called subfunctions. Okay, so let's look at an example. Very simple example. Let's look at the left-hand side first. So in this case, we have a function, right? And let's see, demo. Yeah, actually, the name of the function is demo sub, and we call it demo sub. That's the name of the function. And we have two outputs, at result and sub_result. Okay, so the function, again, this demo sub function is going to add and subtract two numbers at the same time. And what it does is, again, it defines the outputs that we want, at result and sub-result. At result uses the function add to add the two numbers, and sub-result uses the function subtract to subtract the two numbers. Now, those two functions, add and subtract, are defined inside this main function demo_sub. So under this demo_sub function, we're going to define the sub-function add. Now, you don't have to tell MATLAB that this is a sub-function. In other words, there's no, there's nothing preceding this saying subfunction or anything like that. You're still going to use the same format that you use for functions. But MATLAB understands that once you define something beyond your main definition, then if you define something else with the function name, it understands that those are sub-functions, okay? So in this case, the first sub-function is called add, which takes the two arguments x and y and puts it in the result output variable after it does the addition, okay? And then the next function that's going to be defined is the sub-function subtract, which again defines the function subtract, which takes two variables and produces an output which is equal to the difference of the two numbers. So as you can see here, the function itself, demo_sub, is computing the addition and subtraction of these two numbers, x and y, but is calling, if you will, two other functions, add and subtract, which are defined inside the main function. Okay, so those is what they call sub-functions. Okay, this is just examples of how you use sub-functions. So if you run it, you say demo_sub, and you give it the parameters 12100, then it's gonna give you the results of the addition and the subtraction of the two numbers in one step. And you can imagine how you can add this to many more functions if you want, sub-functions, to create other more repetitive things that you may need to do in your program. So that's the idea of sub-functions. Now notice here on the right-hand side, it's exactly the same function, same code that you have on the left-hand side, except for one difference here, and that is the use of the n command here, or keyword, if you will. And it's not really needed when you define a function, right? Functions, like in this case, we didn't use it, but it's a good idea to have it, especially when you create sub-functions, because by using them, for example, here we have an n corresponding to the main function demo_sub, and there an n corresponding to the function add, and an n corresponding to the function subtract. So although it's not required, as you can see, because it runs without it, it makes it even more readable and more user-friendly, because now you can clearly see where the sub-functions are, right? You can clearly see where it begins, where it ends, begins and ends, begins and ends. So it's a good idea, especially if you have the use of sub-functions in your programming, and the result will be the same. It won't change anything. Okay. So let's look at some important things to remember before we slightly move away from the user-defined function concept. Both script and function files are safe with the extension .m. That is why they are sometimes called M files. The first executable line in a function file must be the function definition line. The variables in a function file are local. The variables in the script file are recognized in the command window. Script files can use variables that have been defined in the workspace. Also, script files contain a sequence of MATLAB commands that we call statements. Function files can accept data through input arguments and can return data through output arguments. When a function file is saved, the name of the file should be the same as the name of the function. A user-defined function is used in the same way as a built-in function. It can be used or called in the command window, in the script file, or in another function. Okay, so important things to remember. So now let's look at ways of controlling input and output. We already have seen a couple of ways to do that. For example, DISP is one way that you can control what you see, right? So, but we're going to look at a couple of things in more detail here. The input function can be used to communicate with the program user, for example. In this case, if you look on this statement here, input, we use the input function, which indicates enter a value, and whatever value is entered is going to be assigned to the variable z. So this will display enter a value, right, because the input tells it to display that. And then once the value is input, it's going to be stored in the variable z in this case. You can say, well, what about if you say enter values for z in brackets, right? If you have more than one value, this will then tell the user to input the matrix in brackets, such as this example, right? Where you have 2 rows and 3 columns. So the first row is 1, 2, 3, 1, comma, 2, comma, 3, and then the other row will be 4, 5, and 6, which will indicate again to the user or to the whoever uses the program that the value should be entered in brackets, right? And of course, just like in the first example, the values entered will be placed in the variable z. Okay. And also, if the data you enter doesn't have to be numeric information all the time. You can enter characters, and the way you enter characters is that, like in this example indicates, you will call the input function, and you will say enter your name in single quotes. So anything that is entered in single quotes will be understood as a character variable, and the results will be placed in this case in x. So x will be then a character variable instead of a numeric variable, like in this case in z. So we used some of this in the previous examples. Hopefully you remember. We also use the DISP function, which can display either characters arrays or numeric arrays. So in this example, right, we have x defined as the numbers from 1 through 5. And if we simply say DISP x, of course, you will see the contents of x. If you want to display a set of characters, we'll simply put them in single quotes, and DISP will then display that information. And the reason I'm bringing this back again, the input DISP, is because at the end of this section, I'm going to show you a piece of code that uses this functions plus all the ones that we're going to introduce a little later, and you can see how they can be used from beginning to end. In other words, if you're asking for user information, how you're going to use that information, how you display that information, and how you save it. We did something similar when we looked into the Power program a few lectures ago, but we didn't do a few of the things that we didn't study at that time, and then we're going to study later today. So we're going to reuse the DISP and the input functions again, and that's the reason why I'm bringing them back again in here. So you can display all of the information on the same line by creating a combined matrix of your 2 outputs. For example, you remember we use this also when we say DISP in single quotes, the values in the X array are, and then we use num to string, which is the function that will change the array of numbers into an array of characters. So now we can see the result as an output of characters, a character of outputs. You can use a combination of the input and DISP functions, and that's a good way to create interactions. All right. So that brings us into the fprint f function. This function, if for those of you that have program in C, you'd be familiar with this function. It's exactly the same function you use in C. In fact, MATLAB is written in C, and that's why you see a lot of this same similarities with the C language. But in any event, you don't have to know that. You don't have to know that from C. What the fprintf function does is it gives you output that is formatted. Okay, it's formatted print function. That's what the short name stands for. Formatted print function gives you even more control over the output that you have with the DISP function. There's not a whole lot of control with the DISP function, but fprintf has a lot more control. The function allows you to control how numbers are displayed. In addition to displaying both text and matrix values, you can specify the format to be used when you display those values, and you can also specify things like if you want to skip a line, if you want to tab, and things like that, that DISP doesn't really give you the method to do it. Okay. So the general form for the fprint function or command is that it has two arguments. One is a string, and the other one is a list of matrices. In this case, you have this general format where you have fprintf followed by parentheses, and inside the parentheses, you're going to have a format string and one or more variables. For example, we define the variable freq, F-R-E-Q, equal to 377 over 2 times pi. Okay, that's the variable definition. And if we type fprintf and in single quotes say the value of frequency is, and I'm going to explain this in just a second, %f hertz. Okay, so what the function fprint is going to do is it's going to display what it says in bracket in single quotes. So it's going to display the value of frequency is something hertz, Hz, right? And what it does is it looks at this symbol, the percentage symbol, and it understands that it is a placeholder. Okay, and a placeholder is what the name implies. It holds the value of a variable. Okay, it holds the value of a variable. So when the fprintf function sees a percentage inside the single quotes, it understands that it has to look for a variable. It tells the code, look for a variable, and that variable is going to be followed after the comma. In this case, since it's only displaying one variable, it's going to display the value stored in FREQ. So FREQ has been defined like this. Then the fprint function is going to display the value of frequency is, and it's going to look for that value in the variable FREQ, and it's going to display it. And as you can see here, this is the result, right? It takes the value of frequency is, and it looks into the FREQ variable, which is given by this number, followed by HZ, right? So that's why you see here, this is called the placeholder, because it replaces what the percentage sign is followed by the percentage signs in your final result here. Okay. Now, also, you notice that we use a letter F, and I'll explain that in just a minute, what that is. Okay. But it's basically telling MATLAB how many decimal places you're going to use. Okay, this F, and we'll see some other ways that you can format the numbers that you see, and that's why you see this is a formatting print function, because it allows you to display or save the results in specific format that you want, whether it's decimal numbers or real numbers, exponentials, or whatever. You're going to save them by specifying the letter after the percent sign. And we'll see that in the next slide. So the placeholder again, is indicated by the percentage sign, and in this case, it also contains this F. It includes formatting information. In this example, this %F tells MATLAB to display the value of the variable FREQ and in a default point fixed point format. In this example, say the default format is going to give you 6 places. That's why in the previous slide you saw 6 decimal places by default, right? Because all we telling the program is just display it as a floating as a decimal point, right? In fixed point format with 6 decimal places. However, you can specify how many places you want, okay? And we'll see that in just a minute. But let's look at this example again, where we have defined W as 377, and then we compute F based on this value of 377. And now we're going to say and use the fprintf function and use it with 2 variables. In this case, we're going to say the value of frequency %F. Again, this %F tells MATLAB, hey, what follows is I need this variable. There's a variable here, okay? And it better be on this same list, after the comma. So this first placeholder corresponds to this variable that has been defined first. So it says the value of frequency %F is going to replace %F by the frequency value, and it's going to give me by default 6 decimal places. And then it says it's equal to %F, another placeholder. In this case, it's going to look for the second variable in the definition. And of course, the second variable is W. So it's going to say it's going to replace the value of W in this placeholder. And again, by default, it's going to give me 6 decimal places. And you can see the output here. So the output after performing this little script here is going to say the value of frequency is, oh, I'm sorry, there's no is. The value of frequency 60 is replacing this number, this variable by the number, followed by 6 decimal places, hertz, is equal to the value stored in W, which hasn't changed here, right? That value didn't change. 377 followed by 6 decimal places, radians. Okay. So study this carefully, okay? Make sure that you understand the concept of the placeholder and the order in which you expect your results to appear. And this, of course, is a modified version of the previous example, right? Where we have included another variable, W. And also notice that I've included the \n here, which is another useful way of formatting the output. And we're going to look into this a little bit more in the next slide. But in essence, the /n, it indicates that you want the output to go to the next line. Okay, so it's going to move the cursor to the next line, then display the information. That's all it does. And you can have multiple of them. If I have 2, it's going to skip 2 lines. If I have 3 \n, it's going to skip 3 lines and so forth. It's a very nice way of formatting the output that you want. But in any case, we also talked about the other formats that are supported by this function. And in this case, of course, we use F for fixed point notation. And by default, again, it gives you 6 decimal places. But if you want to see the answer in exponential notation, we'll replace it by E. Or if you want just to display decimal notation, we will use D. And so forth. And there's other ones here. If you want to use character information, you use C. If you want to use a string of characters to display the entire string, you use S. Okay. And so that determines, how you want to see the information from the variables you want to display. Okay. And this is the other special format commands that I mentioned briefly in the previous slide. Of course, we have the \n for line feed. We can also use /r, which is similar to /n. /n is more commonly used. /t for tab, and you can also backspace, okay, if you need to. Okay. So again, those makes outputs very readable, especially if you are outputting something or saving something to a file and you want to keep the information readable and very organized. Then it's not the same thing as if you have everything following one single line, but you can use tabs and line feeds to keep everything organized. Other things that we can do as far as formatting is we have control over the size of the information we see and the precision in which we see that information. In other words, the number of decimal places that we want to see. And for that, we have two formatting commands. We have the width field, which controls the minimum total number of characters to be printed. We'll see how that makes sense in just a minute. And it always must be a decimal, positive or decimal integer. Okay, and we'll see how that works. The precision field is preceded by a period and specifies the number of decimal places after the decimal point. And this is for exponential and for fixed point data types. So the precision field basically tells MATLAB how many decimal places you want to see. Okay, we'll see an example, a few examples in the next slide. So in this one, again, we have our function, the same example that we had before, but now, remember in the previous case, we didn't tell MATLAB how we want to see that information, right? We know that we told MATLAB that we want to see the information as fixed point. And we didn't tell how many decimal places we want to see. So by default, it gives us 6 decimal places, right? So now we're going to tell it how we want to see this information, right? And how many decimal places we want to see. Do we want to have more space after frequency than what we see here? Do we want to have more space after 2 here and then the number 377? Well, we can control that. And then we can also control how many decimal places we're going to see by the width field and the precision field. So again, the same example, but now the only difference is that now I have, after the percentage sign, I have 10(2) F, and for the W or the radians, I have 3(2) F. Now, the concept here doesn't change from the previous cases. I still have a placeholder for this variable and a placeholder for this variable. And I know that the value is going to be displayed as fixed format, right? Or, in decimal, I'm sorry, it's a real number. But then I'm telling it, okay, the 10 tells it is the width field, and is saying to use space for 10 characters followed by 2 decimal places, okay, to display the contents of this variable. In this case, I'm telling MATLAB to save or to use a space for 3 characters and to use 2 decimal places, okay? So if I run this little command now with this placeholders in here, with this formatted placeholder, it's going to display this information, see? it says now the value of frequency, and now you see a lot more space than before, right? Between frequency and the actual value. So that's what the width field does. It controls the minimum total number of characters that are going to be printed. So you see a little more space in there if you need it, of course. Sometimes it's useful when you tabulating information. But again, it's using 2 decimal places, and again, in this case, is using 3 characters, a space for 3 characters, and 2 decimal places. Okay. Another example, in this case, same little program, but now I'm using 5 period 3 for the first variable, so it's going to give me only 5 character spaces, right? So it's a little tighter now, see? But now I'm asking it to give me 3 decimal places. And now to make it even, to generate even more space, I use 15 here for the width, right? You can see it's a lot more space. And I'm using 2 decimal places again. One last one here. I'm using 8 for the width, 1 for the decimal place. And in this one, I kept the, I used the 5 for the width of the area of the space that I want, but I defined the format as decimal, so that W is displayed as just a decimal number. You see here, no decimal, or no period, or numbers after a period here. It's just a decimal number. Okay. All right. Something else to remember when you are using this function: if the variable is a 2-dimensional matrix, MATLAB uses the values 1 column at a time, going down the first column, then the second column, and so on. So, for example, if you look at these definitions here, right, we have W now is a vector, and it includes 5 numbers, right, from 120 through 377, and it's the same program that we've been using as an example, where the radian frequency is then computed as the hertz frequency, right? And what we've done here is we created another matrix called convert, which is a concatenation of these 2 vectors, right? The W vector and the frequency vector, right? So, you know, if you look at convert, right, doing this is actually, you know, showing you this case, right, where it takes W, the definition of W, right, and then takes the results of fric, and it puts it on the next row, right? So that's what this concatenation does. It concatenates 2 vectors to create this matrix, right? So this is nothing new, I hope. But now, to show you what fprintf does, is that if you look at now the use of the function here, it's going to look at, again, understanding what's inside convert, right? We know that convert created this new matrix, and it's saying, well, use a width of 8 characters with 2 decimal places for the first element in this matrix, and for the second element, use a width of 6 with 2 decimal places, right? For the output. Remember, this is this function. I'm sorry, this matrix convert. I'm not displaying this at this point, right? When I'm display it, it's going to display this information in a way that I'm telling it with this function. Okay, I hope that makes sense. So as you can see here, it's taken, as we said at the beginning of the slide here, if the variable is a 2-dimensional matrix, MATLAB uses the values 1 column at a time, going down the first column and then the second column, third, fourth, and fifth, right? And I'm showing you this convert matrix just so you understand what the if fprintf function is doing. So when the fprintf function runs, again, it's going to take, it's going to look at the first element here, convert, right? Which in this case is 120, and it says equal to 19.10 in this case because I'm using 2 decimal places. And then it's going to go to the next column. It's going to say 150 is equal to 23.87. Next column, 230 equal to 36, and so forth, 0.61, right? And you see how the fprintf function is grabbing the elements of this matrix, going one column at a time. Okay. All right. Now, another important function to use is the fopen, fclose function or command. These are very useful when we want to open a file, when we want to create a file, when we want to write information to a file, and so forth. So we use fopen to open a file, specify the character encoding, and obtain a file ID value. When you finish reading, it's a good idea to close the file. And to close the file, we use fclose with the name of the ID of the file you open in parentheses. So in this example, if you look at the format here for the fopen function, right? We use fopen, and then in parentheses, we're going to have the name of the file that we want to open. Okay, so this, in this case, is a text file. Then the name of the file in single quotes, of course, is the file we want to open, and is followed by the permissions that we want to have with that file. And there's a list here at the bottom. I'll explain that in a minute. There's a list of permissions. Okay. In this case, we have in single quotes again, WT, meaning to write. We're going to open. We're going to be able to write to that file, and it's going to be open as a text document. Okay. If we were to have WB, it'll indicate you want to open it in binary mode. Okay, which in this case is not what we want, so that's what we have WT. So again, the way you use this, I want to open a file, right? The name of the file that I want to open is this, and I want to open it so I can write to it as a text file, and I'm going to assign it a file identifier, and that file identifier is going to be saved in this file underscore ID. So depending on what I want to do to the file, I use this different permissions in single quotes. And the list is here. I'm not going to go over all of them, but like if you want to just read it, but you don't want to change anything in it, you just put R in single quotes. W basically does the same thing as WT. It opens a new file for writing, but anything that it's going to discard anything that is in it if you have something in it already. R plus is going to open a file for reading and writing and so forth. And you can see those are the most commonly ones that I use, R and W, for reading or writing to the file. Okay. Some files you want protected, right? You don't want to write to them, you just want to read them and so forth. So let's look at, we're going to look at a couple examples in just a minute. So, in fact, what I want to do now is look at an example that I told you before, where we use the previous knowledge that we have about getting information interactively from a user. We use the display function, the ISP, and we're going to then save that information in a file, and we're going to format the information that we want to save in that file in a specific way. Okay, so I'm going to show you this example, and I'm going to follow the same technique, if you will, that I suggested a few lectures ago that you follow when you're writing code. In this case, what we want is a simple program, but follows the steps that I mentioned before. So we want to find the distance traveled by a freely falling object and plot the result. Well, we're not gonna plot it in this specific example. The main reason for that is that I'm not interested so much in the plotting part, because the plotting will be easy. But what I want to show you is I want to find, or want to write the code to find the distance traveled, but then I'm interested in really saving the information in a file. Okay, not so much plotting it, but saving it to a file. And so what we have is in our way of creating these programs, I'm going to have as input the value of g, which is the acceleration due to gravity, which is provided by the user, and the user is also going to provide the time. Okay, and then the output in this case could be the distance versus time, but instead of a plot, I'm going to display that information in a file. Okay, so we're changing this slightly to see the results display in a file in a certain format that I want to see it. So the output is a file that contains the distance versus time information. Okay, that's the only difference. So we want to develop a hand example. Remember, this is the equation that will give us the distance, right? So a simple hand example tell us that, if our math is correct, given these parameters, at 100 seconds, the distance will be 8,000 meters, right? So again, it's always a good idea to develop a hand example as much as possible. And so the next thing is just to simply develop the MATLAB simulation, or the MATLAB solution, I should say. So in this example, we're using several of the concepts that we introduced, including the fopen and fclose commands that we mentioned in the previous couple of slides. So let's look at this, with a little bit of time here. Of course, this is a free fall example. We want to place the results in a text file, and we want to name that file results. So instead of plotting it, which actually plotting it will be easier, right? What we're going to do is we're going to compute the results and put them in this file called results. So first thing we're going to do is, after we clear the display and the variables and everything, the workspace, we're going to request input from the user. And again, here's where we use the input statements, right? Or the input commands that we used in the past. So we're going to ask, what is the value of acceleration? And we're going to put that in the variable g. We're going to ask the user to enter the starting time, and we're going to put that in the variable start. We're going to input the ending time, and we're going to put that in the variable finish. Then we're going to input the time increments that we want to calculate the information on. And we're going to put that in the variable incr, and we're going to create then a time vector that goes from start to finish in increments of the variable that you enter, the increments that you want to see. Okay. And so the next thing we want to do is use that information that was entered using the input function to calculate the distance, right? We have the equation for the distance, and we want to create a matrix of the output data, right? And so we created a matrix with the two vectors, the time vector that we just created here, and the distance vector that we computed with this equation. And we have this in a single matrix. Now we want to send the output to the command window. So for that, we're going to use the ISP so that we can see that information. And what we're going to see is distance traveled in free fall. And we're going to see time, the S distance, and M. Okay, it's going to display that on the when we look at the command line. And that's fine. And that way you can see the progress of your code here. But the main thing we want to do is that we want to really what we want to do, our main purpose here is to actually, now that we computed this matrix, right, that we know has the information for the time and the distance, we want to save that information into a file when we call results. Okay. So the first thing we're going to do is we're going to use the command fopen. Okay. And we're going to write to a file that we call results. Okay, we call that results, and we're going to identify that file with this variable name file underscore ID. Okay, so now we're going to use the fprint to write results to the file that we just opened. Right, we open that file. The file is open, is ready to be written to. So now I'm going to use the fprint command to write the results of, that I have from output into that file that I created. And I have two fprint statements here. And the first one here is just sort of a heading for the information that's going to follow. Okay, so the first thing I'm going to have in the file is open, and I say, in single quotes again, for an acceleration due to gravity of holder here, 5 characters and 1 decimal point seconds. So the first whatever that result is of G here is what's going to be displayed. Then I'm going to have a line, right? In the next line, I'm going to say the following data were calculated. Again, I'm going to have another line, and I'm going to show the result of G, right? Which is the holder for this variable here. Which is the variable for this holder, right? So that will be the first thing I will see. I will write to that file. Now remember, I'm not seeing the file results on the command line because I'm writing into a specific file. I'm not seeing this in the command line. If I want to see in the command line, I will use something like the ISP, right? Which I'm not doing here. I'm just writing to a file. So the next thing I want to do is I want to use fprintf again, and this time I'm going to use the ID that was assigned to this file results that I created, in which I have permissions to write to, and I'm going to use the formatting since I know I have 2 pieces of information, the time and the distance. And I have 2 placeholders, right? Which the output takes 2 placeholders. And remember, we just look at one example like this, where we had the columns. This one, remember, is basically the same thing, where we have 2 vectors, and it created a matrix. So it's the same thing here, right? So this statement is going to look into the file that I just opened. I gave it the name results, and I have permissions to write to. And I'm going to start putting information, and I have a placeholder, and I have 8 characters with 0 decimal places, and it's going to be a floating type. And then I have another placeholder for the second variable that I want out of output. So one is time and another one is distance. And as soon as I do the statement, it's going to put that information into this file that I define as results. And then the last thing I'm going to do is I'm going to close it. Right? Once it's done, I'm going to close it. Okay. You won't get an error if you don't close it, but it's not a good idea to keep it open. Okay. So whenever you finish with the file, if you're either writing or reading from it, just as a last thing to do is to use the fclose command or function with the name of the file you want to close. See, so once we run this, you can see that again, I'm not seeing these results on the command line. I'm seeing these results going into a file that is called results. This file, and it's a text file that was created by this script. And as you can see, it contains the information that we just run. And this is just another example of a different run, just to show you different values for different values of gravity, and for different increments of time in here, right? So this will be well, unless we change the name of the file, if I run this once, it's going to store the information in that file results. When I run it again, it's going to overwrite this and it's going to instead have this. So unless I change the name of the file, if I keep running it, it's just going to overwrite because it's not protected at that point. I can write to it, every time I run it. So please study this piece of code carefully. Make sure you understand what's going on here, and it shows pretty much a few of the other things we've been doing. So take a good look. All right, and I think that's all I have for now, and I'll see you on the next one.